force is a vector. Your vector arrow will always oppose the direction you're headed. Anybody know who this is?
I'll take it.
20 feet?
Oh, yeah, that's not mine. Hold up.
Like beats and stuff. That must be from my physics class.
Wait.
Okay, sit. So this is just what I've been talking about. If I have a car, okay, and the car is driving down the road that direction, which direction would your friction force be going? Down, or opposing it. Now, if I'm going at constant speed, what's true about the friction force? It's equal as the force propelling it. If I'm accelerating, does that mean I have no friction? Okay, so this is really important. Let me show you this. So this is like the force of my engine, or the process that through the tires and things like that causes me to propel forward. Okay, this is my friction force. This is when I have balanced forces, which would cause what? Constant speed, which is the result of? Right? Balanced forces, no acceleration, so you're at constant speed. So let's say my friction looks like this. Am I accelerating? Yes. Okay? Still have friction force. Just because you're accelerating doesn't mean that you have no force. It's just not equal and opposite to your engine's force. And when you step on the gas, you're applying more of an engine force or less of an engine force depending upon what you're doing. There are 4 types of friction. We're only going to focus on 2. I'm going to give you all 4, but we're only going to focus on 2 of them. Okay. Kinetic is probably one you deal with a lot. And if you're moving, like if a car is moving, that's going to be your kinetic friction. Now listen. Static friction is stationary. So what does that mean? What does that tell you? So you're saying you have friction even though you're not moving? Yes. Everybody hear what I just said? If you're not moving, you have friction. That friction is what's causing it's what's trying to resist your movement. And we'll talk about how the strengths of static versus kinetic are actually different. Now, I'm not going to talk really about rolling or fluid. Fluid friction is just dealing with, fluids, liquids or gases. Okay, I'm going to spend most of my time talking about static versus kinetic. And before I really get too much into that, here are some things that affect how much friction you're going to have. Okay, so all one is saying is you have to have contact for friction. If you don't have contact, you can't have friction. The second slide, or second bullet there, says different amounts of materials create different amounts of friction. Can somebody explain this from everyday life that maybe you have experienced or seen where the type of material has changed the type of friction, or the amount of friction, or the strength of the friction? What? Can you give me an example? Okay. So you're saying, yeah, heavy box sliding across the floor versus a lighter box sliding across the floor. The heavier box has more friction. Okay. Anything else?
Well, what about just paper versus sandpaper? Like, if you can touch paper all you want and like rub on it, it's not going to hurt you. But if you rub on sandpaper, it can actually cause cuts and all that stuff.
Yeah, the material of the surface plays a big part in that. Have you ever went ice skating?
Yeah.
Maybe it's probably better saying that you're not ice skating, you're just walking on ice. Right? If you try to walk on ice, or if you run and then slide, right? You can slide a lot further than if you try to do that on the surface of ground, right? Probably face plant if you try to do that on the ground. And the reason why is, the smoother the surface, the less friction you have. The more jagged or rigid the surface is, the more friction you have, which is why sandpaper is a great example of that. Now, I know you're probably thinking, well, this looks about as smooth as you possibly can get. But guess what that looks like at a subatomic level? This is what your desk looks like at a subatomic level. And so if you put another object that looks like that on a subatomic level, are you going to get friction? Yes. I know it's kind of weird to think about, but remember, we're talking small particles here, right? So the type of surface that you have is going to determine how strong the friction force is. All right, a couple other things. This is more what you're talking about, Ethan, right? What you're writing down now. So it says increasing the force pushing an object against the surface increases the friction. So he said a heavier box versus a lighter box. The heavier box experiences more what? Friction. Okay? So what is the force that might cause friction then when I'm thinking about, when we talk about heavier objects, it's not necessarily the mass. There's a force that's related to mass of an object. Weight. Okay? So if you weigh more, for example, remember, weight is a force. Okay? The more you weigh, the more gravity forces you on the ground. That make sense? Okay? So the more you weigh, the more friction you have because your force is pushing down on the ground. Let me give you an example. Just take your hands and go like this. Now what do you notice? Getting warmer, right? And that's the result of what? Now push your hands hard together and do it. What do you notice? It gets a lot warmer. Because what you're doing is you're creating more what? Friction, because you're increasing the what? Well, yeah, in this case, the force. I wouldn't really call that weight. Does that make sense? Okay? Funny story. We were doing that one day, being stupid or something like that after practice in college. And I had this really like strong, buff teammate, and we were like trying to see like who could like get the hottest, and then we like touch each other with it. And he did it. He like put it between his legs and like really made like a strong force, and he was doing it. And when he showed his hands, he had like blisters because he had like burned his hands. That's crazy, isn't it? Kind of stupid, but crazy. We laughed at it. Fourth thing. This one, when you read it at first, you might go, oh, that's true. But then if you think about it, I think you'll understand why this is true. Or at least experience should tell you that this is true. Just read number 4. It says, the friction between stationary objects, or static friction, is greater than moving friction. So if you're standing still, you have a greater friction force than if you're moving. Up front, that might seem like, really? But then if you think about real life, does it start to make a little bit more sense? Can someone give me an example?
Okay. The ball is coming to you, you just catch it and stop it. But I don't know.
Is it like because you're stationary?
Oh, okay. You have something to add? Ever tried to push an object? And like when you start pushing it, it's like really hard at first, and then once it starts moving, it like almost feels like it's easier to push.
Yeah.
That's because of this. Like you're trying to make a big snowman, and you got a big snowball, and you try to start pushing it, and you push and push, and finally you get it just dislodged and start moving, and then as long as you keep it moving, it's a lot easier to push. I mean, you've probably experienced that, right? Maybe not with the snowball example, but with something. Okay? And I'm not going to pull it up because it's kind of back there all like stuck together. But in physics, we actually graph this. We do an example of this, and we have, this would be over time, and then this is your friction force. And all we do is we take this piece of wood and we apply a force vector to it, and we pull the piece of wood. And this is what it looks like. is the static force, the maximum force you would need to get it to start moving. And then as soon as it starts moving, the friction force is what? It drops, it's less. Okay? So we have actual data evidence that support that. It's not just something we experience or notice every single day when we try to push an object. It's not that we just know that from pushing an object it's harder to start pushing it as it is to keep pushing it. Well, we actually have evidence to prove that. Pretty cool. And it's back there, but I don't want to pull it out. All right, second type of force, probably the force that you maybe are least familiar with. Of all the main types of forces we're going to talk about, I have actually already talked about this, but maybe haven't called it that. You guys have a normal force acting on you right now. Gravity's force is called gravity force. Good guess. So when I say normal, it's not what we would think of in everyday English. It's a different. It means something different in physics. Okay, so it does not mean it's a usual force, although it is pretty common. Here's what I mean. So what does it mean? Perpendicular to the surface, 90 degrees. You guys have a normal force acting on you right now. What is it? What? Talked about it yesterday too. Talked about action-reaction pairs. Chair. The chair is pushing up on you. That force is perpendicular to the surface of the chair. Right? This is your chair. Right? And you're sitting on the chair. I'm not going to try to draw a person sitting on a chair. Okay? We know gravity pulls the person straight down, correct? And the chair is pushing with an equal and opposite magnitude straight up. Do you see how, here's my surface, do you see the 90-degree angle here? So normal force means perpendicular to the surface. Every surface exerts a normal force. What if I have it at a slant? And I have an object here. Gravity's always straight down no matter what. But the surface will always exert a force perpendicular to it. So your normal force will be that, 90 degrees. Everybody understand 90 degrees, right angles? You guys good with that? Is that something you've heard before? Okay, so it's not like foreign. I mean, that's part of the reason. Yeah. Like if I'm not at that slant, you see now how the normal force doesn't completely balance out gravity anymore? And that's why you roll down the hill. Let me see, before you put this in, let me read it. Okay, yeah, put this in. This would be beneficial. That's kind of a lot, but it's kind of telling you, right? You've got your Newton's third law here. You've got gravity that's pulling you, pushing you straight down. Then the object or the earth or your chair or whatever it is that you're on, whatever surface you're on, is going to push you straight up at a 90 degree or perpendicular to that surface. Where's Everett today? Hey guys, you guys are doing good on homework. I don't have any missing now that I had a student turn in some assignments today. Except for Stephen, your lab. Oh, that's the only thing.
Adam, I think it's this
Oh, I'm saying what I've actually graded. Yeah. So,
What are we gonna do about the worksheet?
what did I say we were gonna do about the work? You're gonna have to get it from me after class, or probably after school. I have to have time to print it. Okay, so this just is, in words, giving you what I said auditorially to you. Okay, anytime you're on a surface, no matter what the surface, if it's a slanted surface, if it's a flat surface, you name it. Anytime you're on a surface, that surface is going to exert a force on you. If it didn't, what would you do? If that chair didn't exert a force up on you, what would happen? You'd have to accelerate, right? Because we know gravity pulls you down. So if you don't have a force to balance out gravity, you would accelerate. And you guys aren't accelerating, so, you know, your chair's getting a little handsy. I understand that. Wow. True. True. Yeah, creepy to think about that. All right. Don't put this in. Did everybody understand the little visual that I gave of if you're on a slanted surface, okay, gravity's still going to pull you straight down, like if that's a ball. Your surface, everybody see it's slanted, so there's my 90 degrees. Okay, that's what this is saying, is that if you're on a sloped surface like a hill, you are still being attracted straight down, but it is slanted compared to the slope of the hill. See what I'm saying? It's saying this gravitational force is slanted compared to the slope of that hill. Then it says the normal force is always going to be perpendicular to the surface, which I have just shown there. I don't think it's worth it to put all that in. I don't know why I put that in. All right, so yeah. If you were literally just standing and not leaning or having a force holding you on a roof, you would roll down the roof. Okay. I don't know how many of you have been hanging out on a roof recently, but probably not recently, but you've been on a roof, you understand. You can't just, be willy-nilly or you fall down. Look at all those forces. Get in here. This is based on how they drew this. These shingles should fall off the roof. They didn't do a very good job of this. And I'm probably just going to confuse you if I explain why. So what you have is an X component of that and a Y component of that. So these two balance each other out, but this plus this, if this doesn't balance this out, which direction would that move? It moved down. So in order for this to actually stay on the roof, your force of friction has to be a little bit stronger than that. Well, that's why it would have a bigger force, right? Because you have a more textured surface. And we said that that's going to lead to a stronger friction force. Yep. All right. It says a carpenter standing on an angled roof of a house. What is the direction of the normal force between the carpenter and the roof? Perpendicular to the roof.
Yeah.
Okay? Not straight up. Here it's straight up, not here. Always perpendicular. As normal means perpendicular to the surface. All right? Have a good day. Moira, will you come see me after school then?
Okay. If I remember.
What?
If I remember, I'm kind of tired, so my memory is like
Okay, well, try to remember.
Oh, Moira. Oh, sorry.
No, you have to have.
something correct. It's like, if how many dogs or something you need to do. That part is all.
It's only like 9 to 11. So one day on Tuesday and one
Next year will be by hours. Now, if you, I don't know what your grade is, right? Sometimes we'll let some certain students take chemistry if they do well enough in physical science, if they have like a need that you can get to do it. Otherwise, it's best to like wait a year and get biology.
Slam his head up.